video feed, so you shouldn't appear in the video. But again, if you have a question, just use your mic and yell at me, and we can deal with that. All right, so our goal for today is to... Well, actually, let me just do this before we even start. Can at least someone say yes that they can hear me?
Yeah.
Okay, cool. Good. All right. So the goal for today is to get through Chapter 10. So what I've done is I've tried to curate it down to the main take-home points so we can basically stay on focus. So we're going to be talking about acid-base chemistry throughout the entire lecture. And so this is an important process, especially in biology, and so that's why we're making it an emphasis over other types of reactions in this course. So, give me a second. There we go. All right. So what we need first, when we start talking about acids and bases, is going to be defining our terms. Right, so what I'm going to try to do, we have about 40 slides to get through, and we usually get through around, 30-ish slides per lecture. So I'm going to try to give you the take-home message from each slide. So you might need to go back and read more later, or maybe rewatch the video, or go through the slides a little bit more slowly. So the first thing we need to do is define what an acid is. So we're going to talk about two definitions. The first is going to be Arrhenius, which is what we see here. And then we're going to talk about a second definition called a Bronsted-Lowry acid. And we'll see that in a couple of slides. The take-home message is that anything is an Arrhenius acid if it produces hydrogen ions, so H+, when they dissolve in water. So an example would be something like hydrogen chloride or hydrochloric acid. And so we're seeing a reaction, so we're showing the forward arrow, it's yielding. We write H2O over the arrow to indicate that it's being dissolved into water. So we start with our HCl gas. We can bubble that through water, and when it interacts with the water, it's going to separate into two products, one of which is going to be H+. And so by definition, this is going to make hydrochloric acid, HCl, an acid. What I have down here is also a couple of things to know about acids. It is good to know them, but I'm saying the main take-home message of this slide is up here. And then also this point here, that acids themselves are electrolytes. Be it they're weak or strong, we'll talk about that, but the take-home messages are everything highlighted on this screen right now. All right, see if I can control it that way. Good. All right, see if I can get the, oops. So if we defined what an acid is, it's a very generic term, right? Put it in water, makes H+. So we also are going to have bases, and then under a similar definition, we're going to have an Arrhenius base, and it's a very generic term. It's going to be any compound when added to water produces the hydroxide polyatomic ion. So a common base used in chemistry is actually sodium hydroxide. You'll see this a lot. So sodium hydroxide is an ionic solid. We see it's made out of the cation sodium and then the polyatomic anion hydroxide. So when you add it to water, it's going to dissociate because it's an ionic compound, and it's going to form hydroxide. That makes it a base. Everything else down here, again, it's good to know, but the things that I'm highlighting are the key take-home points. So it would be this one right here, the second point. So they're also an electrolyte because they produce anions when dissolved in water. An interesting side note, though, maybe I'll make this a different color. So they feel soapy and slippery. The reason for that is not because the compounds themselves are slippery, it's because they're actually attacking the fat in your skin and converting them into soap. So if you've ever seen the movie Fight Club and they stick their hands in lye and to make soap out of humans, it's exactly what's happening, and that's actually why it feels slippery. So a weird kind of morbid definition, but that's actually why bases feel slippery. Oops, sorry. Still getting used to some of this stuff. All right, so we have our two definitions. We know what an Arrhenius acid is and an Arrhenius base. What we're going to do is increase our sophistication a little bit about acids and bases by definition. So Bronsted-Lowry acids and bases, Arrhenius acids and bases are very generic. Bronsted-Lowry acids and bases are going to be a little bit more specific. So when we're talking about Bronsted-Lowry theory, it's saying that an acid is going to be donating a hydrogen. So it's a little bit different than talking about when it's added to water, it creates H+, right? Here we're going to be talking about things that come in pairs. So acids are going to be donating a hydrogen, and then bases are going to be accepting hydrogens. So it seems like a very minor detail, and it is, but it adds a little bit more sophistication to our definition. So the example that I have down here, right, we could take something like water, and then if we had that acid that is an Arrhenius acid makes H+. Well, in this case, we're going to have what is effectively a Bronsted-Lowry base, a Bronsted-Lowry acid. So we have something that is donating the H, that's our acid, and something is going to accept that H, and it's water. And so we can see here there's a bond going to be formed between the water and that free H+. And then for us, this is going to be really important, this particular ion here, the hydronium ion. So the reason why I make a point of it, so H3O+, is that free H+, and this is the reason why the Arrhenius definition is a little bit shaky in the terms of it doesn't describe reality. It's useful, but H+ is not going to exist by itself in solution. The reason for that is a free proton is very unstable. I think it's between 3 and 6 minutes. It will spontaneously just decompose into quarks, and those quarks then decompose into something else. So it literally falls apart. The way that it becomes stable is to form a bond with water forming hydronium. And so if we want to take it a little bit further, use another example, we'll have something like hydrogen chloride again, or hydrochloric acid. It's going to be the donor of that H, and what you see in the figure here is that little white sphere. That's our H. And that green sphere is going to be the chloride. So it's going to give its H to water, which is going to make it the base, or the Bronsted-Lowry base, because it's accepting. And then we're left with our two products, hydronium, which is H3O+, and then chloride. Another way, I don't think the book touches on this too, to check if you've done things correctly. If we look at the total charge on the left-hand side of the reaction, HCl is neutral, water is neutral, the total charge is 0. And we see the same thing over here on the products. So hydronium has a +1 charge, chloride has a -1 charge. If I add up all the charges, I still have 0. So it's another indication if you've balanced a chemical equation when you're dealing with Bronsted-Lowry acid bases correctly. So how are we doing with that? I know it's different, interrupting or anything like that, but are we okay with our definition so far? All right, so I can't see you guys. Can I get one person at least just say yes so I know I'm not just...
Yes.
All right, cool. So, great, awesome. I just want to make sure I'm not, wasting your time by talking into the void. All right, so that was a Bronsted-Lowry acid. We were saying, or at least I was saying, that they come in pairs, right? And so we're going to have a definition for a Bronsted-Lowry base. So our Arrhenius definition, that was just making OH when dissolved in water, right? Here, we've already defined it as accepting. So accepting an H+ from whatever the acid is. So an example, if we wanted to visualize what a Bronsted-Lowry base would look like in a different scenario, so we have something like ammonia, so NH3. We're going to talk about this in a couple more slides, but water can act as both an acid and a base, which makes it incredibly useful, and your body takes advantage of that too. A lot of the chemistry done in biology is all acid-base chemistry. So if water actually donates, wrong tool. So if water actually donates the H+, the ammonia can accept it. And again, what we'll see here for tracking our, let me go wipe everything so we can see it again. We have 3 white spheres here, so that's our 3 hydrogen. 2 white spheres here, there's my 2 hydrogens from the water. We have 4 white spheres now on the ammonium. It's exactly what we see here. And now only 1 H on the hydroxide. And again, if we keep track of our charges, both ammonia and water are neutral, so a charge of 0. We have ammonium, which is a polyatomic ion, has a plus charge. Hydroxide, another polyatomic ion, has a minus charge. So 1 plus minus 1 is still 0. So it's another way to double check to make sure things, we've balanced things or at least interpreted things correctly. And so I'm just going to pretty much skip over this slide. This is for everyone, so you can print it off on your own or put it into your notes. But I'm just going to highlight a couple of things that I think are probably the most important. It's going to be our definitions for Arrhenius and Bronsted-Lowry for both acids and bases. Knowing if they're electrolytes, both are. Why are they electrolytes? Well, they're producing charged anions and cations, right? Either producing H plus or OH minus. When you have anions in solution, that solution can then conduct electricity, which makes it an electrolyte. Everything else here is mostly additional information, but we'll come to it towards the end. We'll talk about neutralization reactions, and I mean, they only come in one flavor. Acids react with bases. So acids neutralize bases, that's what we see on the bottom, and then bases neutralize acids. It just means the same thing. And I think most people are familiar with that. All right, so again, remember, if you have questions or anything like that, just yell at me because I can't see the chat right now because I'm using different functions. So to, ask questions, or if I'm going too fast or anything like that, just let me know. All right, so if we have our definitions now, what is an acid? What is a base? So if you've probably heard the term, I'm sure everyone has, of DNA, the A in DNA is literally the word acid. But you have each cell, which is a crazy thing to say, has 1 meter of DNA just wrapped up inside of it. It's incredibly tightly wrapped up. But you're not dissolving, right? It's because DNA is a weak acid. However, and you can eat DNA. I mean, you do it when you eat meat, right? You cook up a steak, or even if you eat a plant, you're eating DNA. But, it's not dissolving you. So what makes something weak? And if I drank, say, HCl, why I'd be having a pretty bad day and have to go to the ER, right? It's because this is going to be a strong acid. It's not very strong, but it's strong enough to hurt. So what makes the difference? Why is HCl strong and why is something like DNA weak? That's what we're going to address. So the biggest difference, I mean literally the difference, is that for strong acids, the acid, keep switching between tools, a strong acid completely dissociates. And so the way we're going to represent that, so just like in that last example I gave you with hydrochloric acid, we know this is a strong acid. It's going to be dissolving into water. And actually, if we, instead of using that Arrhenius definition, if we use our Bronsted-Lowry definition, so if this is a Bronsted-Lowry acid, the reaction has to come in pairs, so water will be the Bronsted-Lowry base. That means this H here is going to get donated to water. It's exactly what we see. We've gone from H2O to H3O, and that's going to leave the chloride left over. So let me just go back a little bit. There we go. We represent fully dissociating with a unidirectional arrow. So it's one directional. So it's basically saying when this reaction is over, effectively nothing is remaining on the left-hand side, and effectively everything is products. That's what makes it strong. A weak acid, which actually is the majority of all acids, only slightly dissociates in water. What do I mean by that? So we take a weak acid like this, which is carbonic acid. So again, we're going to have our pair. There's my Bronsted-Lowry acid, just happens to be weak. Water, again, will act as the Bronsted-Lowry base. So that means one of these two H's, one of them is going to be donated to the water. Again, H2O to H3O plus. And then if I keep track of things, I have two H's here and one H here. The biggest difference, well, the only difference, again, between a strong and a weak acid is going to be the partial dissociation. And the way we show partial dissociation is by using an arrow that's double-sided, which is basically saying the forward reaction happens, then some of the backwards reaction happens, and some of the forward happens. So it means it is going to be less than 100% here, less than 100% here. How much is on each side is going to depend on how strong that weak acid is. So take-home message, right? 100% dissociation for strong, and then it's only slightly dissociated when it's weak. So what does this look like if we graphed concentrations of things? So it's saying we just defined what a strong acid is. Oops, keep forgetting to switch back to my tools. It dissociates 100% into ions. So what's going to do is make a large concentration of H3O+, and then whatever that anion was. So again, if we go back and take a look at HCl, there's my strong acid, there's my conjugate, there's my base, H3O+ and my anion. So there's my strong acid. If we look at the figure on the right, this is before reaction. So everything is in the form of, in this case, hydroiodic acid, so HI, another strong acid, just like HCl. When the reaction is complete, all of the HI is entirely converted into either hydronium, right? Again, hydronium. That's our H3O+, because free protons are not stable. They can exist, they're just not stable. And then it has our anion, I-. So that's what if we want to visualize using a graph. What does it look like? And if we did the same thing visualizing weak acids, and it's actually, the contrast is very stark. So again, a weak acid. If we start, and again, I'm going to take that carbonic acid here. So there's my weak acid, there's my base, forms hydronium, and then whatever, we'll talk about it in a second, it's called conjugate base. But if I start, again, looking at the figure on the right, this is before the reaction. Everything's in the form of hydrofluoric acid, or HF. But when I allow it to dissociate, actually only a little bit of that HF has been consumed. So if we maybe get rid of that highlighter, you can see the small difference. Some of it has been converted into hydronium and fluoride. This is what makes it weak. So that's a really good visual representation of the difference between a weak, and we go back a slide, and a strong, where everything gets converted into products. All right, how are we feeling so far? We've got through 2 sections, a little bit quick, but are most people okay right now? Let me just get yes, someone. Yeah. All right, cool. Yeah. All right. So let's keep going on then. So acid-base equilibrium. So what we haven't touched on, let me go back a slide, is that double-headed arrow, the one that we showed for weak acids. That is what we're going to call an equilibrium arrow. So we're going to use this chapter kind of to like take a lot of ideas and then distill them into one example. But equilibrium arrows do not just have to be for acid-base reactions. They're just common. So what do we mean by equilibrium? And that's what we're going to get into on this. So what is equilibrium? And I think you guys have probably picked up on this by now. When you see the flash on the screen, that's me switching over to my writing tool. So when we're talking about equilibrium, if we break down the Greek, this one probably is not too bad. I don't know what brium means, but equi means same. That just means that the forward rate of reaction equals the reverse rate. So that's why you have that double-headed arrow, because it's telling you that if you have something, say like hydrofluoric acid and water, sometimes the reaction goes forward, and what that will do is make my hydronium and my fluoride But every once in a while, these two will smash into each other and the reverse reaction will happen. And so there's going to be a rate that describes the forward and a rate that describes the reverse. When those two are equal, that's going to be our definition of equilibrium. Effectively, nothing will, if you don't mess with that system, nothing will change until the universe literally dies. And so here what I have is written a little bit more explicitly, right? This is what I wrote on the top. But if we have our forward reaction, there's our hydrofluoric acid, reacts with water to make fluoride and hydronium. But if we imagine the reverse reaction, instead of this being the products here, which are fluoride and hydronium, let me do this. If we imagine them now as reactants, fluoride, which is now going to be a base, can react with hydronium, which is an acid, and then reverse that reaction as well. Again, it's going to be a battle between the forward and the reverse. And depending on how strong the acid is, it depends on what side wins out. And I want to make clear too, right? Equilibrium is not just for acid-base reactions. It's for any reaction. Actually, it's for all reactions. Some look like they go entirely to completion, but it's actually, for most reactions, you cannot go entirely to 100% completion. It's only partially complete. And actually we will never go beyond that. So that gets me into what happens when equilibrium is reached. So just like I was saying, there's no further changes in the concentration of reactants and products. Why? Because the rate of the forward reaction is equal to the rate of the reverse reaction. So there's my forward, there's my reverse, there's my equilibrium arrow. And if I look at this as a graph, so I have concentration on the y-axis versus time, and the definition of rate, and we've seen this before, so delta is going to mean change, brackets mean concentration, and then I'll use delta to mean change again, and then time. And that actually is telling me the rate of the reaction is actually the slope at every single point. And it changes, and what we're seeing is it slows down as we go from point 1 to point 2 to point 3. Eventually, that reaction, the two rates are equal. And when we see that, they're going to be parallel. And so if we monitor the concentration, that means I start with some kind of reactant, and if I look on the graph, I have 0 products. So that would be like having everything loaded up here, but nothing on the product side. I let the reaction proceed, and then what we're seeing is the products are actually being created, which is what you would expect, and because of the law of conservation of mass, the reactants are now being consumed. And again, at a certain point, the rate of those two reactions will be equal, so the concentrations no longer change, because this is being produced as fast as it's being consumed to remake this. So basically, you've matched the two sides, is what you've done. If we want to think of it in terms of like a seesaw, right, we had a lot of reactants and no products. So if we had a seesaw, the reactants are heavy. Eventually, equilibrium is reached at some concentration of reactants and products. They don't have to be equal, because we can see here there are two different levels. But effectively, they're no longer changing. So how do we describe this, and how can we predict how things will change? Once a system is at equilibrium, it's pretty easy to mess it up. If you let it sit there, it'll stay like that forever. But it's pretty easy to mess with equilibrium. And what do I mean by mess with? It's usually by altering the concentration of either the reactants or the products. There's other ways to affect it. We don't go into that class, but I'll just let you know that temperature and pressure are two other ways to affect if a reaction will go forward, will a reaction go backwards. So we state this as the Le Chatelier's principle. What this is going to say, and I'll show you in a second using visualization exactly what it means. But what it's saying is that it's the state when equilibrium is disturbed. So it means I started at equilibrium and I've done something to mess with it. Usually that's changing the concentration of reactants and products. The rates of the forward and reverse reaction will change, and they're going to try to relieve the stress. So don't think of it as like human stress, but by stressing the system, it's by, if you have some sort of reactants, an equilibrium product, if I increase one side, well, the other side's going to have to decrease, to basically keep that analogy of having a balanced seesaw, where we have our reactants and products. So, let me show you what I mean, because sometimes words can actually be confusing. Pictures are sometimes easier. So we take a look here. We're going to start at equilibrium. And then what I'll do in the next figure is I'm going to mess with it. This is what it means by stressing the system or disturbing it. So the stress. What's the stress? I dumped in a bunch of H2O into one side of the container. Here, what you can see is there's some water here, some water here. It's at equilibrium because the level of water is the same. Nothing's moving. I dump more H2O in. Well, now there's too much on this side and not enough on this side. And we all know what happens here. The water's going to flow from high to low until a new equilibrium is reached. This is a macroscopic example. And by, again, macro being big. Sorry, that's channel 5. That's like looking at this is a big example. The same thing happens on the microscopic scale. And that's going to be the small, right? So that's when I'm talking about the actual individual chemical reactions. Oh, running out of time. So I realized I'm going to hit about 40 minutes right now. What I'm going to have to do is I'm going to log out. I'm going to stop the video. We've been going for about a half an hour, but I logged in 10 minutes early, and I only have 40 minutes. So what I'm going to do is I'm going to log out, immediately email you the new link, and then have everyone jump back on. Once everyone's back on, we'll continue the lecture. So sorry it's a little bit of an, disruptive right now. I'm trying to figure out the best way to do this. I have plans, I just haven't been able to execute them yet. So what I'm going to do is I'm going to stop the recording,